Okay, this is paper 4.2, October, November 2021, and its question number 3 is, one of the assumptions of the kinetic theory of the gases is that all collisions involving molecule of the gas are elastic. State what is meant by elastic collision. A collision in which kinetic energy before collision exactly equal to total kinetic energy after collision. So we will write a collision in which total kinetic energy before collision is equal to total kinetic energy after collision. Mean kinetic energy is conserved. State two other assumptions of the kinetic theory of the gases. So the first one, the important is intermolecular forces are negligible. And the second is pressure is exerted due to collision of molecules with the wall of container. Next, a molecule. A molecule, just one molecule of an ideal gas has a mass m and is contained in a cubic box of the side L. The molecule is moving with a velocity u towards the face of the box that is shaded. The molecule collides elastically with the shaded face and the face opposite to it alternatively. Reduce the expression in terms of the m, u, and L for the magnitude of the change of the momentum. Look in this direction. Momentum of the molecule is mu. After collision, it's moving in this direction, and its momentum is minus mu, same velocity in the opposite direction because the collisions are perfectly elastic. So the change of the momentum is the final momentum minus the initial momentum. So the answer is 2mu. So 2mu, you can write also negative 2mu. Next, the time taken. The time between consecutive collisions of the molecule with the shaded area. So suppose this is the surface. One collision is occurring here, then it's traveling in this direction, then coming back. So between two consecutive collisions, the molecule has to cover distance L this side and then L back. So total distance covered will be 2L. Now the velocity is magnitude in same opposite direction. So the distance is equal to speed multiplied by time. Hence time is equal to distance divided by speed. So the answer is 2L over U. And the next, the average force exerted by the molecule, single molecule, force is equal to change in momentum divided by time. F is equal to 2mu divided by time is 2L over U. This 2 cancelled. So we can write mu over L times U. Hence the answer is mu square over L. Next, the pressure on the shaded face. If the force N3 is exerted over the whole area of the face, the pressure is equal to force divided by area. Now the pressure force is equal to mu square over L divided by area of the shaded length into width, mean L square. So it becomes mu square over L cube because L square and L cube. When the model describes an B is extended to 3 dimensions and to a gas containing n molecules, each of the mass m, traveling with a mean square speed c square average, it can be shown that PV is equal to 1 by 3 nm mean square speed, where P is the pressure exerted on the gas and V the volume of the gas, with the expression together with the equation of the state of the ideal gas to show that the average translation kinetic energy of a single molecule in an ideal gas is given by this. Look, equation for the state of the ideal gas is equal to PV is equal to nRT. And from this equation, PV is equal to 1 by 3 nm mean square speed is equal to nRT. Now it can be written as m mean square speed is equal to 3 times nRT over capital N. Now to make this side kinetic energy, multiply both sides by 1 by 2. So it becomes 1 by 2 m mean square speed is equal to 3 by 2 nr over capital N into T. And remember, nr over capital N is the Boltzmann constant, because this number is equal to number of moles multiplied by Avogadro's constant. This is the number of the molecule. This is the number of moles Avogadro's constant. So this nr over this small n number of moles Avogadro's constant cancelled. R over Na, mean molar gas constant, divided by Avogadro's constant is Boltzmann constant. So this is the average kinetic energy of the single molecule, and this is 3 by 2 kT, hence it is proved. Now the next is, the mass of the hydrogen molecule is 3.34 into 10 power minus 27. Use the expression for the EK to determine the root mean square speed of the molecule of the hydrogen at 25 degrees Celsius. Okay. So 1 by 2 m mean square speed is 3 by 2 kT. It means mean square speed is equal to this 2 cancelled. So this is 3 kT over m. And VRMS is equal to 3 kT over m under root. Now substitute the values 3 times, and the k value is 1 point. Boltzmann constant is 3.38 into 10 power minus 23, and the temperature, this 25 plus 273.15. So it is 298.15 in Kelvin, divided by masses given 3.34, 10 power minus 27, and then under root, and after calculation, it is coming approximately 1.9 into 10 power 3. So this is the question number 3.